but 2 cents on holidays. Sadly, though, I'm not a holiday professor. I am a, well, actually, I am a professor. I'm not a holiday instructor. I am a mathematics instructor. So let's talk about some math, specifically discrete math. Honestly, my favorite type of math that you guys haven't been able to tell. Yeah. And we are still talking about induction, as we will all week long. Already with this. There we go. We are talking about weak induction right now. And by the end of class, hopefully we'll understand why we call it weak induction versus strong induction. And it's weak in the sense of the things you get to assume, not in the sense of its power to explain things or be awesome. If anything, it's stronger because of that. I guess it's kind of like, I don't know. Weak induction is more mentally strong, where strong induction is more physically strong. I don't know what you consider more strong. But anyway, the point is, let's just get going. So I've written down on a nice sheet of paper here what weak induction looks like. And remember the whole idea, we had dominoes, actually I had Jenga blocks last time, but the whole idea of like the dominoes chain reaction we were talking about is that if you have a claim that works for all integers greater than some number, right? In this case, I'm saying that for all integers greater than or equal to this random number a, P of n will be true, or P of n some property. Maybe it's saying that, you know, n is greater than something. Maybe it's saying that n is divisible by something. Who knows? But it's just some claim about n. And the proof goes like this. You say proof by weak induction on n. You prove the base case is true. You prove that P of a is true. And then you show that for all n greater than or equal to a, if P of n is true, then P of n plus 1 is true. And if you've shown that, then what you've really shown is you've shown this, I have a Sharpie. You've shown a chain reaction, right? You've shown that P of 1 implies P of 2 implies P of 3. Actually, I guess this should be P of a implies P of a plus 1 implies P of a plus 2 implies P of a plus 3, on and on indefinitely. You've shown that, and you've shown that this is true by the base case. So you know the first part of your chain is true by the base case, then every part of that links via the inductive step. So you've proven that every integer greater than that is true, or it has this property. That's kind of cool. Apparently I have rhythm. Anyway, so this is a weak induction. So we're just gonna do a bunch of proofs and try to really cement this into your brains. I guess it's like if you see like people with wet cement put their hands in it. That's what I want to do right now. Your brain's a bunch of wet cement, and I'm gonna put my hands in it, and let's learn induction. So that was weird. Let's go with this claim right here for our first proof. So the first claim I want to prove goes like this. Any questions, by the way? About induction, not the weird things I say. Cool.
All good.
So the claim goes like this. N factorial is greater than 5n for all integers greater than or equal to 13. Greater than or equal to 13, which I write like that just to give us practice with writing things formally. And if you're watching at home, give this video a pause and try to do it yourself. This one's easy though. All this is saying is that we say n factorial is greater than 5n for all integers greater than or equal to 13. And notice this is kind of weird. And we had a problem in the homework like this that trips some people up. And it's weird because we have the for all part after what we're talking about here. But do not let that fool you. That's just a quirk of English, right? In English, the way the grammar works, you're kind of allowed to introduce things before or after you talk about them. You can say like my amazing math instructor, Daniel, or you can say Daniel, my amazing math instructor, right? You can go either way. That's fine. All depends on context, things like that. It's kind of like if you've taken any foreign language, right? Like the order of adjectives is really weird. Like we would say like, oh, this is a small red marker, this one specifically. But the French might say like, oh, this is a red marker small or something like that. I don't know. French was a long time ago for me. But the point is, different language systems have different orders in which they introduce things, and sometimes it's fluid. English is one of those. But mathematics, like precise logic, you can think of that as a language system, right? It's symbols that mean things, but it has a much more precise meaning for everything, and you can't really screw with it as much. And so one thing in logic, you always need to introduce the variables before you talk about them. So even though English makes sense to introduce in after you talk about it, in logic we need to say for all n in the set of integers greater than or equal to 13, n factorial is greater than 5. And by the way, the set of integers greater than or equal to 13, you could write this as just the set of all integers such that x greater than or equal to 13. Yeah, so a little practice there, but this is what we're talking about here. And by the way, if you notice, we've never ever actually defined what a factorial is. So I'm going to do that right now in front of everybody. So any questions on this, by the way? This is a give and take. I don't want to keep giving and giving and giving without you even having a chance to take. Okay, so factorial, and I'm going to underline fact. This is a fact about factorials. And this is the definition. So for all n in the natural number, so integers greater than or equal to 1, n factorial is defined to equal the product from I equals 1 to n of I. And a lot of you guys have seen it before, but this is it using the notation of product that we talked about a few times ago. And remember, what this product means is this means you do the sum, or no, sorry, is the repeated product of this term right here as I ranges from 1 to n. So when I equals 1, I is just 1. When I equals 2, I is 2. When I is 3, I is 3. And we go all the way up to n. So this is that, all the way out to n. So this is what n factorial means. It's 1 times 2 times 3 times 4 all the way out to n. So for example, let's go pink or red. For example, 1 factorial is just the product of everything from 1 to 1, which is just 1. 2 factorial is the product of everything from 1 to 2, which is 2. 3 factorial is the product of everything from 1 to 2 to 3. 1 times 2 is 2, times 3 is 6. 4 factorial is the product of everything out to 4, which is 1 times 2 times 3, which you found is 6, times 4 is 24. 5 factorial is 1 times 2 times 3 times 4 times 5, which is 1 times 2 times 3 times 4, which above we found to be 24, times 5 is 120. And it goes on like this. That's a factorial. And fun fact, hope this makes sense. I'm going kind of quick because I think most of us have seen this before. Stop me if you haven't. Stop me if you heard this one or haven't heard this one. So yeah, so that's a factorial. Fun fact about factorials, and you guys will learn this next semester if you take combinatorial, which I highly recommend, really fun class. The fun fact is that n factorial represents the number of ways to pick n different items out of a hat. So if you had a nice, do I have a hat with me? I don't have a hat. But if you had, I have some hats up there, whatever. If you had a nice hat, right, with a bunch of crap in it, with a bunch of things in it, with items in it, let's say in was 3 with 3 items in it, there'd be 3 ways to pull things out of that hat. Like if you had ABC, you could pull out ABC, you could pull out ACB, you could pull out BCA, you could pull out BAC, and you could pull out CBA and CAB or whatever. I think I actually nailed that. The point is there's 6 different ways you can pull those things out of the hat. That's what in-fact what represents. Also fun, or that's not what it represents, it just happens to be what it is. Also fun fact, 5 to the n represents the different number of ways to pick in things out of a hat if there are only 5 things that are replaced after every pick. So in factorial, that's the scenario where there's different things in the hat and you're just picking them out until you're out of things in the hat. 5, and the number of ways you can do that. 5 to the n represents the number of ways you can pick out of the hat in the scenario where there's basically, imagine like you just pick in things and you go, but after every time you just replace it. So if I have like 1, 2, 3, 4, 5, let's get rid of these 2. If I have 5 markers here, right? This is the number of ways where I can pick a marker out. Oh, I pick green, and you put it back. Next pick is orange, I put it back. Next pick is pink, I put it back. Next pick is orange again, I put it back. The point is, in that scenario, we always put it back, but it's just the number of ways you can do that. That's going to be 5 to the n. So really what this question is saying is that for all n greater than or equal to 13, it seems that the number of ways you can pick in things out of a hat and not replace them is bigger than the number of ways that you can pick in things out of a hat. There's only 5 things and you always replace them. This is combinatorics. You don't have to know this. I just wanted to show you this to show you that this kind of stuff actually has some real world applications. We were talking about, especially in computer science, we were talking about like the number of different ways things to be sorted and things like that. Combinatorics comes up a lot, and probabilities come up a lot and things like that. And induction can help prove things about it. You thought we were just screwing around this whole time. I'm actually teaching you knowledge. So between the fun, we actually learn useful things.